I'll try to prepare the handouts for Wednesday, and during the weekend I try to make a whole handouts, and then I'll ask my publisher, who has been working with me for the last 20 years, I'll ask him a low price for you guys. Then I have to figure out how many books I have to prepare. You have to check, okay? We don't have to make any extra books. Okay? You have to make a correct count, okay? Okay, let me start by saying our department is Material Science and Engineering. Science and Engineering. That's rather strange, isn't it? For example, electrical engineering, right? Mechanical engineering. They never say science, civil engineering. On the other hand, the physics, okay, chemistry, of course we have chemical engineering, but basically these fields, academic fields, is about the science. Okay, this part is engineering. But our department, Material Science and Engineering, the materials, they are called the scientists in some part and the engineers in some part. Why? The scientists, they are working, doing research just because it's interesting. Just because they have a curiosity on the things, on the phenomena. Engineers, they cannot do the research just because of the interest. They have to have a solid goal for their research. Why are you doing that? Why are you doing this? Something like that. They have to answer very clearly for the engineers. But the scientists, they never answer that. Why do you do that? And they usually say, I thought it's interesting. I'm very curious. I want to know why. Something like that. Okay? So the engineering and science, after the first industrial revolution, which is in 1920, early 1920s, science and engineering has been distinguished. This is the science and this is engineering in 1920. And in 1980, going through 40, 60, and in the advent of 1980, science and engineering get very close. Something like this. Because the scientists, they cannot do the research just because of their curiosity anymore. They have to have a clear vision, clear purpose, clear goal for their research. Otherwise, they cannot get any research fund. Nobody supports that crazy scientist who is working just because of their curiosity only. Okay? And also, the engineers, peoples are very sick and tired of evolutionary progress. You know, people want revolutionary change instead of evolutionary change. And engineers, they just doing kind of a modification, correction to make a better performance, to make the tools or materials for better performance. They cannot really change the essential, basic, fundamental aspects of the phenomenon. They don't have a time for that. So engineers usually make evolutionary progress. But you know, the science and engineering becomes very big changes in recent years. People want revolutionary changes, and they come to know that revolutionary change can happen only when we understand the basic, fundamental aspects of the phenomena. Okay, so the science approach to the engineering part, and an engineering approach to the science part, naturally. So after 1980, science department and engineering department, they just get together. It cannot be separated very much. But material science and engineering, from the beginning in 1920, material science and engineering, it used to just, we cannot distinguish these two, because we have to know why to make the materials more functional to our needs. Okay, so understanding of why is related to the science, but once we come to know the real reason for the materials behavior, then we have to artificially do something to make the materials more stronger, make materials lighter, whatever. Take advantage of understanding the basic physics. And that is engineering. So material science and engineering, they are dealing with the defects, while the chemists and physicists, the scientists, they are working on the perfect materials. If the material is a solid, then we call that the physics. If the material is a gas or liquid, then we call that as the chemistry. Okay? But in the material science and engineering, no matter what, is a gas, a liquid, or a solid, we don't care about it. We're just working on the defects of the materials, the surface of the materials, dislocations, whatever. You know, we want to know the function of the defects or the effect of the defects on the material properties. Once we come to know that, then we want to utilize it to make the materials stronger, lighter, whatever. Okay, that is engineering. So, essentially, we have to deal with the science and engineering in both aspects of the materials. So this is a very unique and very, in this respect, material science and engineering. I like the material science and engineering in this respect. Okay, when we distinguish our human history, okay, we had a Stone Age, and then we have a Bronze Age, and what do we have? We have an Iron Age, and now what do we call this? We a new Stone age, because the silicon is nothing but a stone, as a matter of fact, right? So we call this a new Stone Age because of the silicon. And all those human history can be distinguished, has been distinguished according to their tools, according to their materials used for their life. Okay? So material science and engineering is that much important. So I think you guys have to be proud of what you are doing now. Okay? Okay, let's see. In this class, we are going to deal with the electrical properties and optical properties and magnetic properties. And electrical properties, we are working on the phenomenon or the response of the solids with the outer input. The energy is about 0.1 electron volts or 0.2 electron volts, somewhere around here. Okay? And in electrical properties, we want to talk about the conductivity of the materials and force, which can be defined as the electric field, and velocity, which is the response with the electric field. And this conductivity is the number of carriers and the mobility of the carriers, things like that, okay? That is the electrical properties that we're going to talk about. So mainly, we have to talk about the conductivity of the materials in the electrical properties. And about the optical properties, we are going to talk about the response of the solid with the outer energies. It's a little bit higher than this, like 1 or 2 electron volts. It's going to be the outer applied energies. And we're going to talk about the reflection, refraction, and absorption. Okay, those three properties we're going to talk about. And for the magnetic properties, we are going to talk about the dia, para, ferro, magnetism. But in the chapters for the magnetic properties, we just going to talk about the phenomenological. Okay. We haven't developed a nice theories on the magnetic properties. It's kind of a magic. So we are not going to go deeply on these magnetic properties. We're going to just make an introduction part of the optical properties. And mainly we want to focus on these electrical properties, and especially the conductivity of semiconductors. Okay, and then junction properties. Which is related to the transistor action. That is our main concern of this lecture. All right, the first part of the book, it starts with the duality of the electrons. Is the electron a particle or the wave? Before we go into details, which one is right, we have to understand that there is some interrelationship between the particles and the wave. Interrelationship between particle and wave. This is very important. Without this relationship, we really have to know whether a particle is, electron is a particle or the wave. Okay? But with this interrelationship between particle and wave, we do not have to really know whether the electron is a particle or the wave. Because if some phenomena can be interpreted with the in the concept of particles easily, then in the concept of the wave, then we just apply the particle picture for that case, for the phenomenon. If the wave is applicable, more easy to understand the phenomenon, then we have to adopt the wave. And then anytime we can use this interrelationship to make that wave into particle, or to make the particle wave particle into wave. So this interrelationship is very important, and we have to we are going to have just two principles which make the particle and wave interrelated. The one is Heisenberg indeterminacy. Determinacy principle. Okay? That is, this is a high school thing. All right? The position and the momentum has to be greater than the Planck constant. Let me just write it down here. Uncertainty in position, and delta P is uncertainty in momentum. And the other interrelationship between the particle and wave is the de Broglie wavelength. This is a very important thing. That is the momentum P is H over lambda. H over lambda. And that is H bar K, the wave number, the Planck constant. And in terms of the particles, the momentum can be represented as the mass of the particle and the velocity, right? So, if you have a particle that is, the mass is m and moving with the velocity v, and you want to describe this into the wave, all you have to do is you multiply this 2, and then you divide it by this with the h. Then what you're going to get is the lambda, right? Let me write in here. H bar. 2. H bar, that is a constant, Planck constant. Planck constant. And then we end up with some k, which is a wave number. And that is the 2 pi over lambda, wavelength, right? So we don't know what that is, but if you have some particles, mass m, and then moving with a velocity v, you know the energy, you know the momentum of this particle, right? And if you want to convert this, you want to express this with the wave, then you just, all you have to do is that momentum coming out of this, just divided by some constant, which is a Planck constant, the magic number. Then you end up with some wavelength corresponding to that momentum, some wave. We don't know, we cannot see what that is. The particle, we can see it. The mass m, something like that. But if you want to express this into the wave, then you cannot see actually the wave itself. But there is a way to represent this momentum in terms of the wave. And that is the de Broglie relationship. So that's amazing, right? And